Okay, good morning, everyone. Uh, Welcome back from spring break. I hope everyone had a good break. So before we start, does anyone have any question?
Not really, but good morning.
Hold on, not really, but what? What do you say? Oh, okay. The homework is difficult. Okay. We can talk about the homework after, the lecture. Um, oh, yeah, sounds good. Anything else? Okay, so we can begin the lecture then. So as I mentioned, we have the lecture notes now, right? And so last time we finished with the like the model, the Black-Scholes model with jumps, and this this corresponds to chapter 1 to 3 in the notes. Okay, so this week and probably next week will depends. We're gonna cover exotic option, which is chapter 4 to 6. Okay, in notes. Let me see, 1, 2, 1, 2. I think it's actually 1 to 7 in the notes. Okay, so so if you have any kind of like questions, or you would like to kind of see further reference, then go to these chapters, the corresponding kind of section in the notes, and take a look. So the materials here will be a little bit more technical. Okay, so the plan, right? The plan is the plan of like how I would lecture is I'm gonna give you the broad ideas of how these options work. And then we'll mention some technical details and explain like certain technical details from these chapters. But like, I won't really go deep into the technical details. But if you have any questions about any, kind of like mathematical ideas in this, feel free to let me know, and we will go deeper into any aspect you have questions for. Okay. But the emphasis here is to kind of give you a broad idea of how things work, and not necessarily like kind of explain everything. Okay, so there are 3 types of exotic options that we will be focusing on. The first one would be Berry option. And the Berry options, right, without kind of loss of generality, let's suppose that we look at the up and out. And the idea is, right, that, so here's time. We have our stock. Okay. And there is a barrier level L, right? That basically, so here's T, for example. The option payment at time T will be ST minus K plus. So that's the regular call option, but with a condition that our option has never crossed the barrier from time 0 to time t. Okay, so the notation, this will be an indicator function that tells us whether the event that we're interested in happens or not. Okay, so put together, right? So this is like a stylized one. This is an event. So here, the event that we're interested in, right, is the maximum of the of the path of our stock price is below L. Okay, so if this is true, right, if this is true, then this will be 1, and we get, you know, the regular payment from our option. But if this is false, right, meaning that, like in this picture, at some point before t, our stock price has gone above the level L, then this will be 0, and doesn't matter, right, how the final, right, stock price behaves with respect to k, our payoff will be 0, right? And so that explains that the name up and out. And as long as you are above the barrier level L at any point before time t, if you're up, then you're out. Okay. So that's the barrier option. Now, there are 3 other different types of barrier. Up and in, down and out, and then down and in. Okay, so I hope the name here kind of explain themselves, right? So up and in is the opposite of up and out. So basically, instead of, right, if you cross the barrier, then you're out. Then here you must cross the barrier before your option has any value, right? So it's called knock-in option versus knock-out. In other words, if you never cross the barrier, then your option is worthless in the up and in option, right? Down and out is similar to up and out, except that now the barrier is below instead of above, right? And down and in works similarly with up and in. Any question about any of these types that you want me to explain more? Okay, so maybe we should ask a question: why barrier options, right? So meaning financially, what do they do that, you know, what kind of idea do they add that a regular, right, vanilla option does not do? So what does a person have in mind, right? A buyer, an investor have in mind when they want to purchase a barrier option? What do you think? Why would a person wants to purchase, for example, an up and out? Or why would someone want to sell, for example, an up and out barrier option?
To ensure that they can sell the stock price at its most maximum value.
I think something along that idea, which is correct, but it's more of a hedging, more of a insurance, right? In this case,
Oh, hedging.
well, hedging not in the sense of like, you know, cover the risk, but cover the loss in this way, right? You see, because, for example, here, let's take a look at this. Where do you think, right? So there's two constants. One is the barrier level, one is K, right? Where do you think K is compared with the barrier? Above or below?
Below.
Below, right? Because if K is above, then that's just kind of makes no sense, right?
Yeah.
K is above, then you must cross over L to get paid. But then if you're above K, then ST is worthless. Okay, so so in that sense, K is below L. If K is below L, right, then intuitively the payoff, the maximum payoff, I mean, this is not quite correct, but max payoff is approximately K minus L, right? While without this barrier portion, then max payoff is potentially K, right? So in other words, right, what this barrier option does is it kind of limit the payoff, because if the stock, right, if the stock is too high, then the barrier will kick in and will make the option worthless. So the barrier options kind of limit, right, the payoff function. Compared to the vanilla version. Is that okay? So in that sense, right, the barrier is there to help kind of limit the exposure, limit the swings, right, of the option, like during the whole trajectory. This actually should remind you of the spread. The spread works in a similar idea, except that the spread directly influences, right, the payoff. For example, right, the butterfly spread, if you remember, right, the butterfly spread, actually, I think they call this K0, right? K1, K2. The butterfly spread, right, does this. So in other words, it limits the payoff to this much. Right? So if the stock swings above K2 or below K0, then you have no payoff. But the point is that the spread works directly on the terminal value, while, right, a barrier option works on the entire trajectory of the stock path. But right, the idea of limiting exposure, right, in the sense that, well, you only want the payoff within this kind of range, can be seen, right, in either one of these types of payment. Okay. Does that make sense? Now, so that being said, right, so there, even though, right, the barrier comes in 4 types, and the type of payoff can also come in 2 types, right? In other words, it can be call or put. So in other words, you have like in total 8 possibilities, right? 8 possibilities. For example, up and in call, up and in put, right, down out, call out, down out, put, etc. 4 of these types kind of don't make sense financially. For example, right, up and out put does not make sense financially, as far as I can tell, right? You can still consider it. I mean, you can still write down a mathematical problem, right? But financially, up and out put may not make much sense financially, right? Do you see why? Because, right, what would a up and out put payoff function look like? It'll be gonna be K minus ST, right, plus and then ST, right, is required to not be above L on the entire path. So let's look at the picture, right? Here's L, right? So you are required not to be above L, right, for the entire trajectory. And at the end of the payment, you're gonna be paid, right, K. So for suppose K is here, right? So you're paid K minus ST plus. But you see, the fact that you're below K here and the K minus ST plus, that does not does not kind of limit the payment in any way, because the stock can be as low as it wants, right? And then you're gonna have to pay the whole the payoff function is potentially as large as K, which is exactly the same as the put option. Okay, so when someone sells a put option, what is it that they worry about? When someone sells a put option, right, what they worry about is the stock can be quite low, right? If the stock can go, if someone sells a put option, that means that, you know, someone buys a put option, actually they want protection under the condition that the market goes down. So someone selling the put option, right, worries about the opposite, meaning that if the market goes really down, then they are in for a lot of payment, right, at the final time. But the up and out actually protects in the opposite direction. Okay, so these two directions together just don't make much sense. So in other words, yes, you can still consider this option mathematically, but I mean, and I don't rule out the possibility that you can go buy this, you know, in real life. I just will be a little bit surprised in terms of like, what is it that the investor wants, okay, in this particular scenario. Does that make sense? So in other words, right, if you have up and out, call is the one to go for. If you have put, that should be related to the down barrier. So down and out, for example. Okay, so that's about barrier option. The other types, right, that we're looking at, that we'll be looking at, right? So here's barrier options. The second type that we'll be looking at is the look back, okay, type option. So the look back options would have to do with the maximum of the whole path. So anything like this will be a look back option. So in other words, any payoff, right? This is phi is any function. Any function that has to do with the whole path of the maximum of the whole path of the stock will be classified under the look back option. For example, you could have the vanilla look back. In other words, VT is just a max. Okay, but this is like the easiest one. This is basically a vanilla look back, but you could have a look back call. You could have a look back put. Sorry, not T, right? K. Okay. So in other words, someone who buys a look back option would have in mind that instead of making the payment only depends on the behavior of the stock at time big T, they would want the underlying to be the whole trajectory of the path. But the underlying would be the max, right? So effectively, they swap S big T with the whole max of trajectory from time 0 to time big T, right? And of course, doing this will change the outlook of the payment. For example, this one will always be higher than the vanilla call because you take the whole max. This one will always be lower, than the vanilla put because again, you subtract the whole max, so you subtract more. Is that okay? But anyway, the idea of a look back option, someone wants to buy a look back option, is instead of kind of pinning their payment only on the final value of the stock, they pin the value on the max of the whole trajectory. Now the Asian option works in the same idea, except that instead of the max, it works with the average. Now, the average, traditionally must be this. In other words, you add up, all the values of the stock from time 0 to time T and divided by the time interval. Okay, but of course, I mean, the essential object here is just the integral, The essential object is just the total value. Dividing by T kind of makes it into an average. But in terms of a functional relation, this is not that important. I mean, when you look at the mathematics, but of course the meaning, is it relies on the average. So we carry the T here. But mathematically, this is the object that really matters. The division by T is just like a decoration. So again, you could have the vanilla Asian option like this. And this one, by the way, is the easiest one to look at among the exotic options. In other words, you were given a question like this, before in your review session. This is very easy because the interaction between expectation and integral is very easy. So that's why you were given the problem like this in the review. The one that really starts to make it more important is along the line of the call and put. Less trivial, This one. So this is Asian call and the Asian put. Okay. So these three types of options are the ones that we'll be considering, in the lecture today and possibly next week. So, all right, what do we want to do with these options? So the plan, So, I mean, as I told you before, once you understand the idea of option pricing and stochastic modeling, all of these guys have, similar kind of plans. So first, is the idea of the model, which here there's nothing to talk about. It's going to be the Black-Scholes model. So done, we discussed Black-Scholes model before, but I mentioned this because in a practical setup in a company, for example, maybe Black-Scholes model is not what they want to go with. They might want to go with the jump model, or they want to go with the Heston model, for example. So that would be something to consider, but here we'll just go with the easiest one, the Black-Scholes model. Second, is what I call pricing by expectation. Okay. So now, actually, after you understand the framework of pricing, then a lot of pricing are pretty simple. The price of any option, will be the risk neutral expectation of the discounted payoff. That's it. That's really it, you know, like in terms of like the whole pricing idea. But there are much more to unpack right behind this. For example, let's take the, you know, look back call. Okay. So this is look back call. Or let's say Asian put. So now you see it becomes much more interesting, because the question, right, what you want to ask is, you want more details than, you know, just this formula, right? You want more details. So you may want, for example, numerical value, right, of V0. So for example, we come up with this model, right, the Black-Scholes model, so that we can do pricing. In other words, if I given, right, if you are given S0, right, if you are given the model S0, K, R, sigma, that kind of thing, then you should be able to come up with the value of V0. Well, how do you do so? Well, the way you do it, right, is via Monte Carlo simulation, for example. Now, so possibly, right, what you want is Monte Carlo simulation. But one thing you want to pay attention to in this case is it's going to be slow. All right, it's going to be slow. What's the reason? The reason is the whole point, right, of any kind of exotic option, right, whether it's look back, Asian, or barrier, right, look at the barrier, is that it depends on the whole path of the stock. In other words, the payoff is always a function of the whole path. So if you want to do Monte Carlo simulation for this exotic option, you need to simulate the whole path. Exotic option payoff, right, depends on the whole path of the stock. So you understand the idea, right? That basically Monte Carlo simulation requires you to keep producing, right? Keep simulating many payoff scenarios. And then we just simply average, right, this payoff under these different scenarios, and then you get your V0 approximation. But if each of these scenario requires, right, a lot of simulation, right, you have to simulate the whole path to get to this scenario, then each scenario itself takes, I don't know, like 30 seconds, right, to simulate. Then that, right, if you have to simulate 1,000 scenarios, that costs a lot of time. Compare this with the vanilla option, right, the European option, where each scenario, because it only depends on the final stock price, right, the terminal stock price, then all you have to do is go to the terminal time and simulate the distribution of that stock price. You don't have to simulate the whole path. Okay, this was the idea of your review, right, of the Friday before spring break, that to simulate any European option, you do not have to exhibit the whole path, which will make your simulation much faster. There's no way, right, to avoid simulating the whole path in exotic option. So there are ways, right, to speed it up by using more sophisticated simulation technique, but that would be not in the topics of this course, right? Like I said, that would be something that computational finance is currently taught by Professor Larson. That course would cover different ways that you can consider to simulate the paths, right, to make it faster. we will still play around with the idea, okay? I will still ask you to do the Monte Carlo simulation for this problem, but do realize that here, you will, unless you know more sophisticated techniques, your computer, right? The program will run quite slowly. So I'll just put a question here, right? We won't address this, how to speed it up. Okay, and I won't address this. But now, so the second approach when we do with any of these problems, right, is going to be one, you use the computer to simulate the value without knowing what the structure behind the expectation is, or you come up with a formula. And this should remind you of the Black-Scholes, right? But I guess I'm not sure what your impression is, but before, I guess the Black-Scholes formula may not impress you that much because you always have simulation, right? You always have simulation, and simulation is pretty close to Black-Scholes. Now, I think the formula will impress you much more because the simulation will be very, very slow and the formula will be much, much quicker. But so here, then it gives you a reason why, right, to see that the formula is much more important in this kind of case, or why like learning the math may be more reasonable in this kind of scenarios than before, or more like kind of gives you more advantage. But of course, the formula here will be much more complicated. Okay, because now what do we have to deal with? Because we have to understand the distribution of the max. Let's say the stock price, which in turn would we related to the max of the Brownian motion. Okay. So just to demonstrate the idea of how this can be very complicated, or definitely not a trivial problem. For example, right, let me ask you this. If you just look at the Brownian motion at terminal time, then you definitely know what this is. This is normal, right? 0t. Now suppose that I just take two Brownian motion values, one at half point, one at terminal value, right? And I suppose I take the max of this. I'm just going to ask you a very simple question. Is this still normal? If I take the max, right? So you understand here, the whole point of, let's say, the barrier option or the look back option requires you to take the max of the whole path. Here, I'm just taking the max of 2 points, which is very, very, very easy compared to take the max of the whole path. I just want to add, right? What is the distribution if you take the max of 2 normal like this? Do you have an answer here? Is it still normal? Well, the answer is no. Okay, no. The distribution of the max of 2 normal will no longer be a normal distribution, right? And actually even working out what these are, what the max of these two normals are, will be quite complicated already. All right. And so if you want to look at the whole max, the max of the whole path, you need some kind of really kind of smart thinking, okay, to work this out. I forgot to mention, right, that this actually has only to do with the look back. If you want to understand the Asian option, then you need to look at the average. So again, something like this. Right? What is the distribution of this? Okay, because if you just look at one point, it's log normal. We understand everything about the distribution of SPT. But if you take the average here, okay, what is the distribution? Because if you don't understand the distribution of this guy, then there's no way, right, that you can take this kind of expectation. So, right, you see how is this guy distributed? How this guy distributed? Okay. But nevertheless, we will have, surprisingly enough, we will have formula, right, for example, the look back option, and we'll see why. But you see that to understand this, we need to discuss something about this object. All right, so all of these are under the kind of the pricing by expectation approach. So we want to understand how to come up with formulas when we take expectation, or how to come up with numerical values. 3 is about connections, right? So this is the PDE representation. Or, as I like to put it, kind of more practically, right? Any of these options, right? If you look at Asian, you can look at Asian or look back, they are functions, right, of the stock price, of the terminal time, of the volatility. So there are Greeks for these guys, right? There is the delta, there's a gamma, there's a theta, there's the vega, for example, for the exotic options, just the same way as there are Greeks for the vanilla options. However, right, when you look at an exotic options, you would not expect that the Greeks behave in the same way as the Greeks of the vanilla options. Okay, for example, right, the Greeks of the vanilla option, the European option, follows the Black-Scholes formula. Do the Greeks of the exotic options follow the Black-Scholes PD? Well, the answer is no, right? You don't expect that the Greeks of the exotic options to follow the same PDE as the European options. In other words, when we look at PDE representations here, the question we want to ask is, how do the Greeks, right? So in other words, theta, right? Delta, gamma, and possibly other ones, right? Vega, for example, of the exotic options interact. Okay, so how do they connect? Maybe let me say connect. Okay, so well, to remind you again, right? For the vanilla option, for the euro option, you have minus RV, right, plus theta, that's V sub t, plus delta times R times stock. So, and then plus 1/2, right, gamma times S square, right, times sigma square is equal to 0. How does the connection look, right, for these different exotic options? All right. So this exactly will be what we will be focusing on. Try to answer these questions right, and try to develop a math for that's the program for these exotic options for this week and next week. All right. Any question about this? All right. So now then let's go straight in and let's start with chapter 4. Okay. And so chapter 4 in the notes, right? If I refer to this is in notes. So chapter 4, the title is the PDE for Berry option. And the one that is addressed is down, up and out. But you can use a similar idea for the other types of options. And so, you know, as the title suggests, for different reasons, as you see, the first object we want to look at is going to be the interaction of the Greeks for the Berry options, for the up and out Berry options, okay, in chapter 4. We'll relegate the question for the expectation in chapter 5 and above. Okay, so even before, right, we jump in and look at the Greeks, there is this concept that we want to introduce so that we will be able to use, you know, in even deriving the PDE, which is a concept of stopping time. Okay, so it's an important concept. It's helpful to, it's going to be very, very important for us to analyze all these things, is stopping times. So first, I'll explain what it is. I think you have heard of it before in Math Finance 1, but it, you know, it's good to refresh your memory. And then I'll explain how it is relevant in this kind of context and even beyond. So first of all, right, let's recall that our setup always kind of have in mind an idea of a filtration behind the scene, the flow of information. The flow of information on the time interval 0 to big T is represented by a collection of sigma algebra. Okay, so this is a collection of sigma algebra where the idea is, right, for s less than t, then the sigma algebra at time s is contained in the sigma algebra at time t. Okay, in other words, right, the more as time progresses, right, so this represents information. So the information represent that you have available at time s will be no more than the information you have at time t, right? So, and a lot of times, right, these objects, the sigma algebra is directly connected to the sigma algebra generated by the prime motion, right? So in other words, knowing this, so a lot of times, right, I don't think this is super important. This is more important to us, but a lot of times, right, the sigma algebra is directly connected to the sigma algebra generated by the prime motion, right? So this is the filtration of the sigma algebra. By the object that we're looking at in the Black-Scholes model, by the prime motion. So what this means, right, really is this, that this really means, all you need to know is that what this means, this guy, right, the sigma algebra contains the information of the whole path of W on 0 to small t. Okay, so in other words, by saying this, all I mean is that, you know, knowing the path of W from 0 to small t is the same as knowing the sigma algebra F little t like this, which of course, right, sigma algebra is just a collection of sets. So it's just a coding, right, of the information represented by the Brownian motion on the time interval 0 to little t. Okay, so I guess this is just a bunch of structures that all you have to remember is the flow of filtration, really, and some intuitive meaning behind this. The concept I want to introduce is stopping times, which, right, is a, so tau, so definition. Tau, right, is a random variable taking values on 0 to big T, okay? Technically speaking, let me do this. It should be taking value from 0 to infinity. Is a stopping time with respect to some filtration. I can't write. You know, let's say infinity. If the set tau less than or equal to t belongs to the sigma algebra ft for any time t. Okay. So again, this, and again, I think I should be grateful for Professor Larson to, I believe that he kind of introduced you to rigorously, right, the idea of sigma algebra. I will not drill you, I will not test you on sigma algebra like per se, but if you want to understand, right, more like exactly rigorously what this statement means, then, you know, what they mean is this is a set, right? The event that this random variable taking values of t or smaller can be exactly known, all right, can be exactly known by observing the sigma algebra generated at time t. Okay, so I'm more interested in the intuition behind this, or the idea. So the idea is this: tau, right, should represent the time of some interesting event that you care about. Okay, which event? I notice I say, right, random event. So what random event what random event do I have in mind in this context? Well, you know, we're discussing, right, Berry options. So clearly, the one of the time that we are really interested in is, for example, the time that our stock crosses the barrier L. Okay, I will put it like this in English, and I'll put the mathematical representation right after. But you see that this time right here. So for now, right, I just want to build your intuition. You see this time right here, there are two aspects of it that I want you to pay attention to. The first is that it's random. In other words, right? So for example, here is the time that our stock crosses the barrier, right? Is here. This is this time. So here is tau, right? It's random because if I have a different path, right? If I have a different path like this, then right here will be tau, right? The time that you cross the barrier depends on how the path looks. So different, right? I think you're familiar with Monte Carlo simulation now, right? The whole idea of the path being random means every time you run it, you get a different path. So if you look at how when the path, right, crosses the barrier, that would be a random. So that's why, right, we are interested in random time. Now, of course, this is kind of easy, but we have in mind, right, the contrast between random time with deterministic time, right? Big T right here is deterministic, meaning what? It's going to be, let's say, June the 30th when the option expires, right? June 30th is always June 30th, right? But if you say when Google stock goes above, let's say 1,800, or when Google stock goes above 2,000, that's a random time, right? It may happen before June 30th, or could happen after June 30th, right? We don't know. So that will be a random time, right? So a lot of events we deal with are random. So we would like to mark, right, those times with a representation. Now, in this context, right, why do we care about this time? Well, we care about it in this context, right? Actually, the question we have, right, is this less than t, or is this bigger than t, for example? Right now, that's something that we care about, right? Because if the first happens, that means our option expires worthless because it's up and out, right? It's up and out. So if tau less than t, that means we have crossed the barrier before expiration. That means, we expires worthless. But if this is the case, then, right, we have not crossed the barrier before expiration. That means we have a chance, right, to be expired in the money. Okay, so I guess when doing this, right, I make the connection between the meaning of the random time with the behavior of the option, which again, right, requires you to be aware of the context of what we're doing. But, right, being able to read this kind of ideas is going to be important here. Any questions so far? So in doing this, right, in giving you the example, I kind of left out a important detail. In fact, right, I just say here the time that our stock crosses the barrier. If you look at my picture, right, there are many times that our stock crosses the barrier, right? It doesn't have to cross only once. So notice that here, when I draw this, I look at the first time that the stock crosses the barrier, right? That's not, accidental. That actually is what I meant. So let me clarify this concept more, right? So here I just want to give you an example, so I don't want to load you with details. But in fact, right, the important point of stopping time is like this, that not all representations of random time are stopping times. Okay, so the requirement of stopping times is this. So anything that is a random variable that take values on a positive line is a random time, because it's just a random variable taking values, positive value. But in order for it to qualify to be a stopping time with respect to some flow of information is this statement. Meaning, right, the idea here, right? So the key, the key is this requirement. So what this means is, right now, tau is a time of some random event. Tau less than or equal to t means the knowledge, right? The event happening on or before t. Okay, this is this piece. By saying that this belongs to the sigma algebra at time t means it can be known by observing ft. Okay. Now, this seems a little bit abstract. Like, what do I mean by observing ft? Well, this can be made more concrete if you think of it as the sigma algebra connected with the Brownian motion. So now what this means is exactly by observing w on 0t. Well, okay. Now let me make a remark. Because our stock, right? Our stock is e to the r minus 1/2, let's say mu, okay? Mu minus 1/2 sigma square times t plus sigma wt, okay? So I hope it's clear that there's a one-to-one relation between stock and Brownian motion. In other words, observing w is the same as observing the stock, okay? So all of these kind of follows the same way. So in other words, when I say observing w on 0 to t is the same as observing the stock. In other words, right, when we look at the path, the behavior of the stock from time 0 to time big t, observing the stock path like this or observing the Brownian motion path will be the same, because I always have a way to translate the Brownian motion to a stock and vice versa. Is that okay? So what I'm trying to explain is not all representations of random times are stopping times. How? Let's look at these two different cases. And let me just use English, all right? So 2 examples. Let's say tau 1, okay? And let me use English here. The last time that the stock price crosses tau 2 is the first time that S crosses L. Okay. Question. Are they both stopping times? In other words, when we say this, right, the implicit understanding is stopping times with respect to the Brownian motion filtration, or the stock price filtration. In other words, what I'm asking, right, is this: do I know, right? Do I know whether or not they happen, right? The event. So the event is the first time, right, the stock crosses L, or the last time that S crosses L. So in other words, do I know that one of these guy, right, is before T by observing stock price on 0t? What do you think?
Yeah, I want to guess that tau 1 is stopping time since like the last time L crosses L.
Okay, that's actually a great guess. Why you think so?
Like that's just assuming that like F keeps on like rising or decreasing until like it reaches L. So like then that's when it stops. So like once it does that, then that's when like F stops. So that's when tau one.
So don't read too much into the name of stopping time, right? I don't know quite well why they call it stopping time, but
Mm-hmm.
so yes, but the difficulty here actually is to interpret the math correctly. So let me ask you a very
Oh.
question, right?
Mhm.
Do you know when the last time you and I will meet? Don't think
Oh.
about but
Oh.
do you know? Do you know, for example, right?
No.
Why
No.
not? Because we can meet, I don't know, 10 years from now in the future, right? At some conference.
Oh, right. Yeah. Mm-hmm.
But do you know when the first time that you and I met?
Oh, yes. Yes.
It was sometime, right? The summer, last summer, whatever.
Mm-hmm.
So you see that actually, even though, right, somehow you pinned it on the last time because you think that the last time is something that is knowable. In fact,
Yeah, it's the other way around,
not be known,
isn't it?
right, by observing the information up to this current time. Because it can
Okay.
always happen one more in the future.
Okay. Mm-hmm.
Does that make sense?
Yeah.
So in fact, right, I hope I explained it, that tau 1 here is not a stopping time. Or tau 2 is a stopping time. Are we okay here?
Yeah, I get it.
Right, okay. So, and does anyone else have any question on this? I hope that the connection, right, with this and this and this is clear. The reason, right, again, is this, that if you look at a picture, here's L. So then this is exactly tau 1, you know this. But is this tau 2? Oh, sorry, this is tau 2, sorry, right? This is tau 2, the first time. Is this tau 1? Not, right? I mean, unclear. The stock could just go down like this forever. Then yes, this is tau 2, tau 1. But if the stock somehow goes back up, then definitely this is not tau 1, right? So you do not know until you have looked at the whole, like, I mean, the infinite path of the stock, which is impossible. So in other words, right, tau 1 is not a stopping time, but tau 2 is. Okay. So back to here, when I say the time that our stock crosses the barrier L, what I have in mind is the first time. The first time. Okay. That would be a stopping time that we will look at. And any questions so far? And the connection, okay, and the connection with our barrier option, the up and out, will be like this, right? So representation of the payoff, okay, in terms of stopping time. So now we will be more formal and we'll put down the mathematical notation. Let tau be the first time, let's say u, t is fine, that st is greater now. Okay. Is everyone okay with the notation of infimum? It's a notation from real analysis. it's a minimum kind of, but it's a continuous minimum. We okay here? I hope. If you want me to clarify, I'll be happy to. So infimum of a set, right, is the the biggest upper bound, biggest lower bound, right? So for example, the infimum of the interval 0, 1 is 0, for example. Okay, so no one says anything. I hope that's fine. All right, so anyway, right, basically here, what we're saying is at any time, the stock price is above the right. For example, anytime the stock price is above the barrier, right, I collect that, and then I look at the least the biggest upper bound, right, of the biggest lower bound of this set, then I will get the first time that my stock crosses the barrier. Okay. All right. So now, so anyway, right, in English, it just translates to the first time that the stock crosses L. Oh, by the way, right, I mean, this is, of course, under the assumption that the stock price, the S0, right, is less than L. You know, I mean, that's just common sense because I look at up and out. If my initial stock price is above L, I'm already out at the beginning. There's no point of looking at the option, right? So that's why, you know, crosses L definitely from below like this. So first time you above. All right. So everything connects like that. Okay. So now remember, right? We said the payoff, right? So this is up and out call. It's going to be ST minus K plus. And then with the provision that my stock, the max of my stock is no more than L. So I claim that this is the same as saying that the event, right, the first time that the stock crosses is after T. Is this clear? Right, because right, okay, I hope, right, because the first time, if the first time is after T, then of course my entire stock must be 4, right, must be less than L. Cool. All right. So, but you know, this is not just beautiful representation. Okay, you will see this again in the following up. All right. I want to take a slight detour, right, to tell you that this is not the only place you'll see stopping time in this class. Stopping times will show up in American options. All right. So American options, the whole point of American options, right, is that the buyer can choose some time between 0 and T, right? The holder can choose some time between 0 and T to exercise the option. And notice I use this notation. So first of all, the holder does not have to pick a fixed date between 0 and big T to exercise the option. The holder can choose a random time. But on the other hand, this random time, right, must be reasonable with respect to the filtration generated by the stock. In other words, right, our holder, unless he's like, you know, some fortune teller, and even if he's a fortune teller, cannot look into the future. In other words, right, whatever decision he makes must be dependent, must be observable, must be knowable by observing the stock price up to and including the present time. What that means is that he or she, that person, must choose a stopping time, right? So this is exactly a stopping time. And so the holder, being a rational investor, will basically try to maximize the payoff. Like this. Okay. So I'm just taking a detour to show you that stopping time will show up when we look at American option, because exactly the whole idea of American option that gives the holder a chance, a choice, right, to choose a time to exercise is reflected in the tau right here, right? If they exercise at time tau, that payoff is S tau minus K plus, right? And discounted back from that time, and the holder will try to maximize the payoff like this. And of course, right, the only requirement from our side in terms of modeling is that this holder cannot choose random times that somehow peek into the future. For example, right, he cannot choose options of type tau, he cannot choose times of type tau 1, that the last time that something happens. That's not available to him because he doesn't know, right, when that time is. But among the stopping times, then he can maximize like this. Okay, so that's another place where you see this show. Any questions so far? All right. So what do we do with this? With the call option, right, with the barrier up and out call option, we converted the payoff representation into something that involves stopping time. But that's not the only place, the only idea that we do this. So in terms of up and out barrier option, the most crucial piece of information, all right, and this is where I say that we may or may not go into the whole details of it, is this. The most important representation is this. Oh, you know what? Sorry, let me backtrack. I have to introduce one more concept before I talk about this representation. So actually, I think this is connected to the use of the word stopping, actually, and I think now I can tell Don that I do remember now why they call it a stopping time. So one more connection with the stopping time is called a stop process. Okay, a stopped process, and I think this is where the stopping time names come in. So suppose you have a process, okay, xt, a process, okay, with respect to some filtration. So the filtration, right, ft is always in the background. And tau is stopping time. Of course, right, with respect to this ft. Now, the stop process, right, this notation. Okay, so here, this I think is the mathematical way to write. You might have seen this before, right? The minimum of two numbers is that wedge, right? Is such that it's quite simple actually. You just read the minimum notation. Okay, so basically is you stop this process at time tau. Okay, you stop this process at time tau. So in other words, here's t. So suppose your x, right, does whatever it does. This is your x. And now suppose tau is here. So this is xt, right? Suppose tau is here. Then the stop process, right, will be from here to here is xt minimum tau. But then it will just be horizontal right after that, because that's x tau. Is that okay? Maybe I can use another symbol to do this. So it will be just straight out like this. It will be the same up to this point, right? But it will be like that. Is that okay? So, right, so that explains the choice of the word stopping. In other words, you use a stopping time to stop a process. Why? You'll see, all right? But is this okay? The idea of a stop process. So again, you will see the stop process a lot, you know, in this kind of exotic option. But the important result here is that a stopped martingale is still a martingale. Okay. So in other words, if you have a martingale, meaning something that kind of moves on average is constant, is the same way, then even if you stopped it, it's still a martingale. Okay, it's still a martingale. So we'll go back and we'll explain this later. But what's the relevance of this for us? The relevance for us in our case is this. Remember, we say tau, right, as the first time that the stock price goes above the barrier. The big intuition, right, that I want to explain to you in the up and out, or in most of the barrier option is this, or at least in the up and out. The important point is only the time interval is relevant to us. Do you see why? So this is not 0 to big T, right? Only from 0 to tau. So what I'm saying is when I study up and out barrier option, the the time, so this is a random time interval, right? This is a random time interval of tau. Only this time interval is relevant to us. Do you see why? Well, so think about it. What happens after tau? What happens after this random time tau? Not only constant mean is zero, right? I mean, well, it depends on what you mean by constant, but if you look at the option value, it's zero, right? Because after tau means after the stock has crossed the barrier, our option is worthless. Doesn't matter what the stock does, right? So here goes back to this, right? So only from here to here is relevant to us. In other words, right, if you were to look at your option value from here to here, then it's still hopeful some value, right? You can still trade it. Can you follow this, right? If you are a trader, right, you can still trade your option up to this time. After this time, how much do you sell your option for? Zero, because anyone, right, with the knowledge of the stock will know that it has already crossed. There's no value to this option. So, right, when you analyze the option, this is only the life of the option. After this, even though, right, the expiration time is big T, is worthless. Is that okay? So this, right, this is connected. So mathematically, the following is happening. This is the following mathematically. What is VT? The option price at time T. Well, so first of all, right, notice the easy and the not so easy way to do things. I mean, first of all, the easy one is always this. That's our universal, right, pricing equation. The hard thing is to unpack this. Well, V big T, right, is, in our case, ST minus K plus. And then let me do this for now, okay? Are we okay? We said this before, right? The stopping time must be above T, right? Now, but here you are conditioning on information at time T. In other words, right, you're saying that I have observed everything up to time little t, wherever little t is. So I claim that, right, the fact that tau is after t means that it must be after little t, and it must be, let me say, how do I say this? Well, maybe let me rewrite. what do I want to do here? Sorry, give me a moment. What I want to do is this. I want to kind of separate, right, the time interval from 0 to little t to the time interval to 0 big T. So maybe let me do this. So what I want to say is this. I want to consider this event. Okay. And I want to break it up to 2 parts. Okay. And then like this. Okay. And so the fact that my barrier, right, has not been crossed from the time 0 to big T is the same as the fact that my barrier has not been crossed from time 0 to time little t, and then my barrier has not been crossed from time big little t to time big T. All right. So that's all I want to say. So maybe is this analysis right here that I want to insert into this. The reason is this, that basically, right, this piece of information is known by time little t. All right. So maybe that's where I want to use maybe not this notation, but this. Remember, right, this and this are similar, are the same. These are the same way. So what I want to do is I want to break down, right, this information into something that can be known by time t, by time little t, and then something that belongs to the future, right, from time little to time big T. So what I want to do is this. I want to say that this is all right. And then this piece right here is still inside because that's the future information. But this right here can be factored outside because it's known by time t. So times okay. And again, remember this is VT, the value of the option at time t. In other words, the only thing I want to tell you is this. It's going to be E tilde, right, of something, condition ft, times, what is this? This is the indicator function that my stopping time is above t, above little t. That's all I want to say, right? My VT, my payoff, right, or my option value at time t is directly connected with the first time the option cross must be above t, right? This is just mathematically I admit, maybe a more complicated way to connect the fact that the only time interval that is relevant to us is from 0 to tau. Because after tau, meaning, right, if tau is less than t, right, that means t is after tau, then Vt is equal to 0. This is what I'm saying. This is what I want to demonstrate, the idea that after tau, right, Vt equal to 0. Or, you know, more rigorously, after tau means if t is bigger than tau, then Vt is equal to 0. Why? Right here. And you can see that what I want to demonstrate to you is, right, all of these comes from the structure of our conditional expectation. that it does fit into the mathematical pieces like this. Okay, that the tau goes along with the VT at every level T. Any question on this? All right. Do ask question, okay? I mean, not much math here, but a lot of concepts. And altogether, basically, the main message is the stopping time here, all right, controls the whole window, the whole language of how we are approaching this barrier option. So if you kind of don't understand what I'm dealing with here, then you'll be lost to a whole, main point. So do ask questions. All right. All right. So what I want to say, right, is that so to recap, right, only 0 to tau is the time interval relevant to us. Okay. So in other words, right, and now I think that's what Mead was kind of thinking, that I was anticipating what I was trying to say, because 0 to tau is the time interval relevant to us. In terms of stock, right, the stock process we care about is ST minimum tau, or the stock process. Is that okay? So in other words, right, as far as the up and out barrier option is concerned, we do not care for the stock price process after time tau. In other words, right, the whole window, again here, is only, so it's like this is the end. We close our eyes. We don't care for what happens after that. Because again, right, why? After this, everything is known, everything is settled. The stock price is worthless. Okay. Oh, sorry, the option price is worthless. So it has a very kind of profound but simple message that as far as the up and out barrier option is concerned, this is like our soft exploration, right? We know the exploration is here, but really, it's just up until the time that it crosses. Of course, if the time that it crosses is after this, right? If the time that it crosses is after this, then sure, the entire path is relevant. But if the time it crosses is below, is before the exploration, then all our windows, the window that we're concerned with is here. Any question on this? Okay. And so now, why is this relevant to us again? Or so now that we put it in the language of the stock process, right? So remember, right, now this is where the idea of a stock martingale is relevant, because, right, our PDE derivation before relies, I would say, heavily or mainly on the idea that the discounted stock price is a martingale, right? If you remember the whole idea of the Black-Scholes formula, right? If you remember, right, the whole Black-Scholes equation, right? Black-Scholes PD is that you look at this. Sorry, right? So which in turn would imply that eta minus RT VT is a martingale, right? Because this will be, right, minus RV plus V sub X, right? RST plus 1/2 V sub XX sigma square ST square. This whole thing, right, dt, and then plus something dWt. And because this is a martingale, this must be 0. Okay, so the whole connection of the Greeks, right? Oh, I forgot the V sub t, right? The whole connection of the Greeks relies on this being a martingale. With the barrier option, right? If you look at the whole time interval 0 to big T, you cannot say that. You cannot say that on, so let me put this down. This is important, right? With the barrier option, we cannot say that eta minus RT VT is a martingale on 0 to big T, right? Why is that? Why can't we say that it's a martingale on 0 to big T for the barrier option? Well, the reason, right, is exactly, again, look at what happens. If, right, the stock crosses L before big T, then V is equal to 0 after this. Now, something, right, that imagine from here to here, the option has value, right, a positive value. And then right after the stopping time, it falls to 0. Does that look like a martingale? Now, again, right, remember, what is a martingale? A martingale is such that, right, roughly speaking, the expectation should be constant, right? Its average value should be constant across the whole time interval you're looking at. So if somehow, right after the stopping time, it drops to 0, that cannot be martingale behavior. Are you okay about that? So, right, the martingale concept is not that mysterious. The martingale concept only means that, you know, the value on average, right, with respect to the filtration is constant. But if you know that after some time, even if it's random, that it suddenly drops to 0, then the expectation over here is definitely not the same as the expectation over here, because this has positive expectation. Are you okay here? So, right, in other words, the same idea that we applied to the Black-Scholes PDE before cannot work in this case, because it's not a martingale on the whole 0 to big T. On the other hand, the modification actually is quite simple. That actually is a martingale on 0 to tau up to the first time that the stock crosses the barrier is a martingale. Why? Why can we say this? Well, I mean, when we say that something, right, is a martingale from here to here, what are we saying effectively? This is because a stopped martingale is a martingale. That's really it, right? That's because a stopped martingale is a martingale. So in other words, when you look at the time in the from, if you kind of look at the time interval from only to 0 from 0 to tau, then it's equivalent to look at this. These two statements are the same. This being a martingale from 0 to tau is the same as saying that the stop process is a martingale, because you're not going to limit, right? You don't care for what happens after tau. So you say that the stop process is a martingale. Is that okay? Question here. Okay. So how does that affect, right, the PD derivation? So what that means, right, for us is that the PD derivation for the original Black-Scholes equation for the vanilla option is like this, but no restriction, right? So the PD, right, for the Berry option okay, is very similar to the classical PD, except that we need to be careful to interpret the fact that it only holds on zero to tau. Okay. So what are we saying? Effectively, right, everything we do here is still the same, because this is still a martingale, but instead of on 0 to big T, it's on 0 to tau. So what that means, right, is that we still have this minus RV plus V sub T plus V sub X R times S plus 1/2 V sub XX sigma square S square. This is equal to 0, except that this is on 0 to tau instead of on 0 to big T. Okay, but let me ask, right, what does this really mean? Because one thing you should be aware of, right, is that in PDE language, there's no random stuff. Okay, in the PDE language, there's no random stuff. In the PD language, it's just going to be deterministic T and X. There's no random connection, right? When you calculate, for example, the Greeks, these are numerical values, right? So when you say, so everything here is fine, but the problem is here on 0 tau. What does that mean on 0 to tau, right? So what that means, right, is what does on 0 to tau means? Remember, tau is the first time that a stop crosses the barrier. So in other words, right, what that means is that this equation holds on 0 less than or equal to S less than or equal to L. Okay. And so here, this is a T domain. This is the S domain. All right. So 0, L. So by the way, are you doing numerical PD in Professor Wu Jun's class yet? Are you studying numerical PD? You know what numerical PD is about? Yes, no, maybe. Anyone? You have not studied numerical PD?
Are you referring to like partial differential equations?
Yeah, but solve it numerically.
Hmm.
No, not yet.
Okay.
Like
Let's see
the wave equation, that kind of thing. No.
Oh yes, I remember that.
Okay. In the
Hmm.
I'm not going to ask you to solve it numerically here. I'm just referring, right, to the fact that when you solve for UTX, I'm not sure that's notation he used. What does it mean to solve for UTX?
It means to define ETX such that it satisfies like a given partial differential equation.
Right, but in terms of like the techniques that you solve it, right?
Mhm.
What?
Oh, you use like its derivatives in terms of t and x, like ut and then ux or uxx, I think.
Yeah, but even more basic than that, you should have a grid, right? You should have a grid point of
The
t,
gradient? Yeah.
x, and then you divide the grids into the grid into so many points, right? And the point is that you
Mhm.
will find the values of u,
Oh, so you divide those like derivatives
not derivative,
into certain.
the the tx plane. So
Okay. Oh, okay.
like basically, what I'm saying is that, so here's the t plane, here's the x plane, and usually you have a domain. You say, I don't know, if this is A and this is B, you have a rectangle, and you would divide it into so many grid, and then you would find the u values in all these grid points. That doesn't sound familiar. Have you done that before?
I believe so, yes.
Okay. Yeah, that's all I want to ask, if you have done that, because it's exactly what I'm trying to tell you here, that
Mhm.
basically for the up and out Berry option, your grid will be here from 0 to big T for the T dimension, but 0 to L for the X dimension, and you would divide into the grid like this, and you solve for it. Except that, right? So basically what happens is when you solve for a barrier, sorry, when you solve for a PDE, Professor Wu Jun should have mentioned something like boundary condition and initial condition. Do you remember something like this at all? So initial condition, right, means, so in terms of this picture, basically you must be able to tell what the values is, let's say on these edges, because this is where, for example, here, this is where x is equal to 0, and this is where t is equal to 0, right? So this is the boundary condition, means, sorry, initial condition means where t is equal to 0 here, and this is where x is equal to 0. You must know these values. Okay, so for the PD, for the PDE for up and out option. The boundary condition will be right here on this edge. This is where V is equal to 0. This is where V is equal to S minus K plus, like that. And there's no initial condition. These are the two boundaries that we look at. Seems strange. Does not connect with what you know from the other course. The difference, okay? So the difference between this and a Black-Scholes PD is right here. So the difference, okay? If you have a Black-Scholes PDE, what happens is you have minus RV plus V sub T plus V sub XRS plus 1/2 V sub XX sigma square S square is equal to 0. That's it. There's no restriction like this because it's just a co-option and not a barrier option. So in other words, when you were to look at the domain, right, of the picture, it will be, so this is S and this is T. This still restricted like this, but you would solve for the value of the stock at any point. No upper bound, no restriction here. Okay, because when you think about it, right, for the call option, right here is S minus K plus. The stock can go as high as it wants. The stock can go as high as it wants, and there's no restriction on how high the stock can go. With the barrier option, this is the effective domain. It cannot go any higher than that. In other words, right, the moment that your stock touches the barrier, your option will start to become 0. Is that okay? So in terms of the Greek connection, that's the difference between this picture and this picture. I hope that makes sense. Any question? So let me ask, right? I don't know because you're kind of quiet today. I'm not sure because it's kind of abstract. So you're still trying to digest the material. Are these two pictures the same in terms of, right? So remember, it's the same equation, right? Okay. So V, the V, the Black-Scholes, the value of the derivative is like the 3D picture, right? It's gonna be, so this is the domain of V. V will be the height, right, upon this point. Okay. So the equation of V has satisfied are the same in both cases. The difference is here, right? V is restricted here. V is, sorry, the S, right? The S direction is restricted here. Here, the S direction is not restricted. Okay, V is a function of T and S. Okay, V is a function of T and S, or T and X, if you will. So do the function V, right, which I'm not drawing here, is going to be the height of this. Are they the same function on both these pictures, or are they different?
They're different.
Okay, I hope that you see that, right? Yes, they must be different, right?
Yeah.
So also,
The other one is not.
what about the Greeks? Are the Greeks the same or different? Are the Greeks the same or different? In other words, if I look at the Greek of a barrier option, right, up and out like this, and the Greek of a Black-Scholes, right, which after all, right, they satisfy the same equation. Are they the same or different? In other words,
Are they
right?
the same?
Okay, that's what I was hoping for. Why are they the same? And by the same, what do I mean by the
Like,
same? Yeah.
I think it's, even though one of them is not restricted and the other one isn't, they still like have the same like this. I feel like the call like still moves the same. Like it would like either increase or decrease depending on like T or X.
Okay.
Yes, I have.
No, it's good thinking, and that you should start from that. But you see that that's again right where you start to kind of try to make sense of this, but you're not really following the math, right? Which is okay. But notice, right? So what I'm saying is like, okay, right? The Greeks are still connected in this way. But when I ask if they're the same or not, I ask if they're same in values, right? For example, let's say at this point, right, at the same point, right, these are same coordinates. Do the values of the Greek equal for these two options? And Dawn, you seem to say that they're the same, right?
Yes.
Oh, sure. Thank you. Now, let me say this, right? Actually, that should make you suspicious because, for example, what's the value
Oh,
of the
they're not the same then.
what was the value of the Greeks for the up and out up here?
0.
Zero, because there's
There's
nothing.
nothing.
What about the value of the Greeks up here?
It's some kind of value, non-zero
Yeah,
value.
it's something, right? Because it still has
Yeah.
value. So already, right, that they're not the same everywhere, right?
Oh, I
So,
see.
but
So
now
like they would be the same if it's like
in the same
less than
domain.
L, but otherwise they're not.
All right. So now let's analyze that idea because, right, again, Don, I really like the way that you're thinking, but the whole point, right, of the trickiness of these things is that you do not want to follow your intuition too fast. So yes, right, your next guess is that yeah, maybe they're the same, right? Like if you draw L here, then they're the same down here, but
Uh-huh.
not the same up here, right? Which seems
Right.
reasonable enough. But are you sure about that?
No.
Okay, because I asked a question. So let me say this, right? Let's meet your excellent. I like that. Exactly. Um, the delta gets pretty negative, I think is really very good observation. And exactly, right? Near the barrier is where crazy stuff happens for the barrier. All right. Now, I think meat really is getting the gist of this because, for example, right, if you look at the imaginary L here, right, which is not there because you know the vanilla option has no barrier. Do you think that the stock or the option behaves differently when it crosses this barrier, when the stock crosses the barrier? In other words, is there any kind of sharp jump in the values across the barrier here, across this imaginary barrier? Because there's no barrier here, right? Is there any sharp change? Should not be, right? Because, I mean, the stock moves smoothly among these. So there's no sharp movement, right? So in other words, if you look at the Greeks below here and the Greek above here, I would imagine they're pretty close. Is that okay? If what I'm saying doesn't make sense, then please let me know, right? On the other hand, look at this, right? Here, when you approach this, right, your option still has some value, right? And it may, for example, look at this. What does this mean? So let me ask this just intuitively. So for a stock price around here, right, for this point, does the option have more value or less value compared to this? This and this, right? So point one and point two. Which point do you think has more value? And there's no right or wrong here, right? It's just intuition. I might be wrong. But point one and point two, which one do you think has more value? in terms of the option value, option price. No, it's fine. I would argue, right, that point 0.2 has more value. I think I might be wrong. Why is 0.2 has more value? Because they start at the same level as, right? In terms of payoff, they're the same. Which one has a better chance of expiring in the money? 2, because it's already very close to the target, to the expiration. Is it okay? I mean, I might be completely off here, but I think that 2 has higher value than 1. Yes, in terms of option value. Is it okay? On the other hand, if in both of these cases, right, if the unlucky thing happened that you cross the barrier, what's the value of the option here? 0 and 0, right? So in terms of the Greek, the delta, which one has a sharper change, 2 or 1? At which point does the option value fluctuate more, 2 or 1? I think 2 right now, because 2 has a higher value. Do you agree with me? 2 has a higher value, right? 2 has a higher value because it's already close to expiration. It has a better chance of. But then when you just cross the barrier, right? They have the same distance to the barrier. They both, boom, go to 0. So the change at 2 is higher than the change at 1. Do you agree? So I would argue that the delta at 2 is higher than the delta at 1. Right? So in fact, the closer you move to the corner here, the more, the sharper the delta would be. In fact, I don't think, right, that the delta would get negative. I don't know, right? But the delta, right, the delta will get bigger and bigger. Actually, I think it's more and more positive as you approach this corner. Because, right, when you think about it, if you are, just put yourself in terms of like the option holder here, right? The closer you get to the corner, the more you're anxious, right? Because you're getting to the best possible payoff. But just a slight jump and you're done. So, right, here is where the stock will be very crazy. But obviously, I mean, anytime you get close to the barrier, the delta will get really, really crazy already. And I mean, for that reason, gamma too, right? So meat is right in the sense that the closer to the barrier, right, the more crazy the delta would behave. But I'm not sure meat also meant this, which is also a barrier of sort, but like barrier in time, right? Exploration. But I'm not sure I agree with meat that it's going to get more negative, right? I think it gets more positive. What do you think, meat? The delta, I'm not sure actually. I do believe, right? Because still, I mean, this is the delta between this. So if you have a small change, right, but it's going to be really large change. Maybe I'm wrong. I don't know. Could it be negative? Because you jump from here to here, go to 0. No, but okay. I think we need to maybe look at numerical example. Somehow my brain is not catching this. But all I want to draw your attention to, right, is that close to the barrier, all right, the Greeks, the delta at least will be very crazy. My intuition is it's gonna be a very delta at that point. Not on the barrier meet. I agree. Very close to the barrier. Right. What I'm saying is as you get closer and closer to the barrier, the delta would be really large, gets larger and larger. Right. That's clear. Sorry, well, big in terms of magnitude. So what I'm not so sure about, right, is that whether it's going to be negative value here or positive, but I'm not touching the barrier, right? Just close the barrier. Okay. Okay, I guess we'll just have to do some experiment, the numerical experiment to look at it. But all right, so but what I want to say now, right, and which is exactly the point, is that, right, even though these two follow the same PDs, right? So in other words, the connection between the Greeks are the same. The individual behavior of these values will be very different for the berry option and the vanilla option because with the berry option, right, the closer you get to the barrier, the more crazy the Greek will behave, meaning like it will get larger and larger. All right. I have to think about whether it's large negative or large positive, but otherwise, like that's what I want to say. Any question here? I still think that it's going to be large positive, but yeah, it's crazy. All right. Well, okay. So that's what I want to say about these two, right? So, and this is also the reason why, like, exotic option trader would be interested in this kind of thing, because somehow, right now you have a different behavior of the Greeks with respect to another parameter, the barrier, right? So by trading, right, options with different barriers, you can kind of trade the action of the option on the delta and the gamma, right, at different levels that you won't have access to compared to the vanilla option. Okay, so the addition of the barrier would change the behavior of the Greeks dramatically, which again, right, would be interesting for the kind of traders who want to kind of operate around that area. Okay, so that's all I have for the up and out barrier option in terms of the Greeks, in terms of the PD. I will assign questions, right, for numerical calculation so that we will see more clearly what happens here. All right, either in the review or in the homework. I think it's a good place to take a break here, and then when we come back, we'll deal with the pricing by expectation. Okay. Okay, so let's continue. I hope everyone's back. Okay. So to recap, right, of let's see, there's a chat. Hello, yes. So to recap what we were discussing, right, the highlight of the discussion before is that on the level of the connection of the Greeks, the barrier option, right, the well, out and up and out, the connection is exactly the same. So the equation, right, is exactly the same for the vanilla and the knockout barrier option. The difference, though, and it's a crucial difference, is that there is a barrier here, which translates to the barrier, right, in terms of the window, right, that our PD behaves compared to, right, no window in terms of the vanilla option. And that in turn, again, right, in turn translates to very interesting behavior as you get close to the barrier. All right. And I want to draw your attention to the fact that, right, there is this barrier, which of course is the barrier, but even here, right, the expiration is another barrier that somehow we don't pay attention to much here in the vanilla option, but we pay attention to here. Why? Because this corner, okay? This corner is a very interesting corner. Now, if you take Professor Wu Jun's class, he might highlight that corner as where, right, things break down. Why? Because if you imagine, right, the value of the option, so I have more time to think about it during the break. How does the option behave going from here to here, right? Option price. You see that it would kind of increase, right, a little bit from here to here, but at some point it will start to decrease because at the boundary, right, at the barrier, it must be zero. And the option being a smooth value, I mean continuous value, right, it will be increase and then decrease. Increase and then decrease, increase and then decrease. Is that okay? At least I think I strongly believe that's the behavior. So in that sense, meat is correct. In the sense, I think close to the barrier, the delta should be negative. I agree with him, right? Now, but on the other hand, there is this movement in the t direction. And then right there, you notice that, for example, right, it's unclear to me how the movement in the t direction behave in general. But you see that what I want to draw your attention is to the fact is that if you have 2 points at the same S value, but one closer to expiration, that one should have higher value. Why? Because it's almost close to the end, right? While here, right, is still far from the end. So in other words, right, you have the rise and fall, right? Rise and fall. I believe that right here, it will rise and then fall quickly because, right, the closer you to the barrier here, the more hopeless you are. But here, it might fall more slowly. Why? Because, right, the closer to the expiration, the more chance you have of expiring in the money. I think, all right, that's just my intuition. But the point is, right, notice that, for example, there is a big tension here at this point, and that is clear. I don't have to have any intuition to know this. Why? Because if you follow this direction, right, if you follow this direction, this is S minus K. The higher you go, right, along this border, the more payoff you have. Agree? But as me pointed out, right, along exactly on this boundary, you get zero. So you get increase and increase here, right? So imagine that if you were very close to this expiration, then the behavior should be similar to this. In other words, increase, and then boom, you hit zero. So there is a discontinuity here. So there's a big behavior, right, happening in terms of delta and gamma and that kind of thing around this corner. Is that okay? So right now, I like to think in terms of intuition because before we jump into calculation, right, we just try to see how the option behaves. And then we do use calculation to make it more precise and back it up. Now, so speaking of, right, in terms of calculation, let's just run a, I don't know, a thought experiment on this. Suppose I ask you to simulate, right? So thought experiment. How would you simulate, let's say, the Greeks of the up and out barrier option? Okay. So two questions. How would you do it? Meaning pseudocode. What would you do? And B, how efficient you think it is? Meaning how fast your conversions will be. What do you think? So first, how would you do this kind of simulation? Can you roughly describe the pseudocode? All right. So for example, suppose you want to simulate the delta at this point. What you have to do, right, is you have to simulate, right, all the stock path going from here on out, right? You have to simulate all the stock path from here on out. You have to check whether these paths cross the barrier before time t or not. Okay. So in other words, you have to simulate so many paths. The path that crosses the barrier, you assign value 0. The path that does not cross the barrier, you assign this value. And then you average out over all those paths. You will get one option value here. And then you would do the same thing to a point close to it, right? Simulate all the paths, assign values, take average, and then you would do the delta approximation. In other words, right, subtract the option value divided by the difference in the stock price. Okay? That's your pseudocode. How efficient is this? I mean, how accurate do you think this procedure will be? So I just described the pseudocode for you, right? How accurate do you think this is? If you were just to do the regular simulation, this is not very efficient. Meaning very slow conversions. If you were just to do, regular simulation. Okay. But of course, right, you see that this kind of finding exact value of the Greeks will be very important for us for several reasons, right? I pointed out that, checking the sign and the behavior of the Greeks close to a barrier is very important to us to understand, right, more precisely the behavior of the option. But even in practice, you see, the whole idea, right, the trader needing like quant like us, right, like you guys, is for you to tell them, okay, here's the estimate of the delta and the gamma near the barrier. So, this is what you want to trade, how much you want to trade, that kind of thing, right? Delta hedging, gamma hedging, right? Those ideas are still relevant here. And without knowing the delta and the gamma, well, how can you do delta hedging and gamma hedging? So these questions are very real. And if you cannot calculate to a satisfactory, right, accuracy for this delta and gamma, you're not very kind of, conducive, right, to the team. So being able to calculate this, right, is very important. And so this, by the way, right, leads to several areas. One area is Professor Wu Jun's class, where you do not have to approach this using Monte Carlo. You can just use PDE, right, techniques, namely numerical linear algebra techniques, right, matrix technique to solve for this, all right, which is a very interesting area, which I admit I am aware of, but I'm not very, proficient about, so I don't know much about the techniques there. But this is why PD is important, because if you want to make it very accurate, well, PD is one way to go. Second, of course, is Professor, Casper's class, right? Professor Larson's class, because, okay, if you want to go with Monte Carlo simulation, the regular Monte Carlo simulation is too slow for you, right? Too slow for conversions. How to speed up, how to change the way you simulate things, right? To make it converge faster. Second area, right? The third area is this class where, well, we don't do this, we don't do that. Frankly speaking, those are, I think, more practical. But what we do here is we'll just come up with explicit formula, all right, for the Greeks, or at least for the price. Okay, we come up with as close as possible for closed form formula, right? So let me say this, right? Ideas, numerical analysis. That's why, right, numerical analysis is valuable. Monte Carlo, advanced Monte Carlo techniques. For us, closed form formula. Okay, and so this is my contribution to your understanding that I will present to you closed form formula. But I'll be frank with you, right? I'm a little bit suspicious about closed form formula, not because it's not correct here. It's very good, and it should convince you, right? The only thing I'm suspicious about closed form formula approach is that I'm not sure how universal it is, because the techniques here you will see will be very smart, okay, very slick, and it seems to me that, well, at least what we'll be discussing, all right. So that's actually chapter 5, pricing by expectation. It's going to be very slick, and you will see that it's beautiful, I hope, but it's limited to this context. While the techniques you learn in these two other courses can be applied to any context that involves PDE or involves Monte Carlo simulation. It does not have to be limited to, look back option or barrier option. It's universal. As long as you can write down a PDE or write down a simulation problem, you can use those techniques. So I do believe, right, these two are more universal. But anyway, right, seeing a closed form formula will also be helpful for you in some way, right? At least if you just care about understanding the classical knockout barrier option, then our contribution here is helpful. All right. So pricing by expectation. So in other words, right, I want to go back to this whole idea right here. And I want to give a closed form formula for this, okay? As close as possible. And then you see the closed form formula somehow involves this guy, right? So let me say this. This is the Black-Scholes part. This is the exotic part, right? And to take expectation of this, what we need is exactly the distribution, okay, of the max. And so we need to understand the distribution of, let's say, the max, okay? For now, let's just do this. All right. Now, what is this? This will be the max S0, right? Let me just write EXP of 1/2 mu minus, mu minus 1/2 sigma squared times U plus sigma WU, right? Now, the max of the product, right, is a product, this is a constant anyway. you can pass this max in. So in other words, it's going to be S0 times the exponential of the max. Like this. Okay. Now, this is where I have to stop, because the max of the sum is not the sum of the max, right? Because, depends on how these two sum interact, right? Depends on the sign, etc. So I cannot put the max in further. But we have a trick up our sleeves. Remember that the whole point, right, of the change of the Gasanov's theorem is that you can absorb, right, this into one single prime motion. So in other words, you could do W prime of t. Let me do this, sigma. Where I write W prime because it's not really our W tilde, right? Our W tilde only absorb the R. Here, sorry, the U is outside. Here, right, the drift is mu minus 1/2 sigma square, or R minus 1/2 sigma square, as you will see. So anyway, the point is that let's not worry about the exact math right now, right? What I'm saying is like you can absorb the drift into a different prime motion by change of measure. So starting out with the barrier option, we need to understand the distribution of the max of the stock price. But you see that eventually, right, the real object or the main object that we want to understand is the max of the prime motion, which is equivalent to the max of the prime motion. W prime, a prime motion. Okay. So, sorry, let me restart my thing. Okay. W prime, a prime motion. All right. So in other words, right, understanding the distribution of the max of a prime motion, or rather we call the running max of a prime motion, will be important to us. All right. So that's the starting point of this chapter. How to understand the distribution of a running max of a prime motion. Okay. And so for that, the main tool that we'll be using is called the reflection principle. Okay. The main concept or the main tool is the reflection principle. And the reflection principle comes in two steps. All right. So first, let me tell you what reflection principle is. So reflection principle is this. That suppose you have a level L, all right? Think of it as the barrier, but because we're dealing with the prime motion, it's not exactly the barrier that a stock has to deal with. It's a modification of that barrier. But for now, let's call it L, okay? Or I think let's call it M. So we have our prime motion, which start at 0, okay? This is W. So forget the prime, right? Just W. So our prime motion would move. Oh, my M is too high. Right, and it will cross the M at some point. Now, after it crosses, right, it will do something like this, okay? The idea of the reflected prime motion, though, and it'll be quite strange at this point, but we'll consider, right, a reflected path of this across level M. In other words, we'll consider this. Okay, so the red line will be the reflected Brownian motion. And the blue line, of course, right, or purple, whatever, is the original Brownian motion. Is it okay? So basically, the reflected Brownian motion, reflected path, at least for now, is that it's the same. It's going to be the same as the Brownian motion up to the first time it crossed. But then at the time, right, after it crosses, we will, instead of whatever the original Brownian motion does, we'll reflect it across the barrier. Is that okay? Across this level. So the first point is this. So let me just call reflected path for now, because you may think that I'm revealing the detail, but it's really right there. The reflected process is also a Brownian motion. Okay. So in other words, if you have a Brownian motion and you and you follow it, and then you kind of revert the path like this, then the new path is not, of course, not the same as the old path. But when you look at it as a law, okay, as a rule, then it still satisfies the Brownian motion rule. So in other words, both of these are two different Brownian motions on this page. Is that okay? So that's the first concept. Of course, right, the question of why we'll address this. But for now, I just want to list out a component that the red path and the original blue path, they're both Brownian motions. Okay. Now, how is that relevant for us? Okay. How it's relevant for us is the following identity right here. So the relevance is this. Okay, the relevance for us is like this. That suppose, right, I call the new path, right? Let me call the reflected path. Let's call it B, okay? B, all right. So in other words, right, B of T will be WT. So the original path, right? The original path is W, and the reflected path is B. Okay. So BT is WT from T to tau, and then it's gonna be what is it? Reflected back, right? So it's gonna be. Let me try here. Let me see. W tau minus WT minus W tau for T bigger than tau. Okay. So this right here, right, is a reflection part. Do you see? Because, right, if it were a plus, then that would be just WT, right? If it were a plus, so this, right, is the gap, W tau, right? So here, W tau is just a fancy way to write M, right? So if you want, actually, it's just going to be M minus WT minus M. Or again, right, it's just really 2M minus WT. But I think writing it like this may be a bit less easy to see in terms of the intuition. This right here, right, tells you that from the level, right, instead of adding the difference between WT and M, which will give you original WT, right, you subtract, hence you reflect. Is that okay? So that's W. That's the reflective ground motion. Okay, and of course tau here is the first time. Tau is the first time that Wt is equal to. Okay, so I'm just laying out, right, the mathematical description of these guys. Now, the importance for us, right, the relevance for us is the following identity. Oh, I need one more notation. Okay, let MT be the max. So this is the running max, right? This is the run. So this is the running max that we care about. This is the guy that we're interested in. This is the guy we're after, right? This is the guy we're after, right? Why? It shows up right here. You see this guy. This is, if you want, this is like M big T. Okay. Now, so, I mean, this is definition, right? The identity I'm interested in is this. Is that MT bigger than M, WT less than W is equal to BT bigger than 2M minus W. Okay. So that's the identity that I'm interested in. That will be crucial for us. All right, so several things, right? First of all, of course, right, why is this true? Which we'll address. But more importantly, right, how is this important for us? How is this relevant for us? Okay. So again, right, I'll address this later. I mean, very soon. But how is this relevant for us? Well, it's relevant for us in this way, that we're interested in the distribution of this guy, right? Well, what is distribution? I mean, I hope you guys remember something like the CDF function, right? The CDF of x, for example, is the probability that x is less than or equal to x. That's called the distribution function, right? Cumulative distribution function. But of course, it's equivalent to this as well, because, you know, they add up to be 1. So in other words, right, if you were to ask for the distribution of a random variable, you can either look at this quantity or this quantity. So right here, right, without this part, this is the quantity we're interested in. Fine. But what is this doing here? Actually, what this is doing here, right, is that it gives us, so let's call this 1, okay? 1 gives us the joint distribution of WT and MT together, right? Instead of, so in the probability language, right, it might seem like you're interested in the marginal, meaning only in the behavior of the M. You say, fine, well, let me give you the joint behavior between M and something else, like this. If you're really interested in the marginal, what do? Well, you just integrate this out, right? You just integrate this out. Or you can take W to be infinity, right? Then if W is infinity, then this is 1. So then you take this out, except that you see that there's some relation between this and this that cannot happen. But anyway, right? So we're interested. So the relevance is that we're interested in the distribution of M. This expression gives us the joint. And by the way, right, when I say we're interested in the distribution of M, I'm not being precise. Actually, we are interested in the joint between M and W, but I did not want it to be, super complicated. So I just point out the max. The reason is bury somewhere here, okay? Bury somewhere here is still a relation, the joint between the max and the W, because like at time 0 you don't see it, but at any other time, let's say you look at the max between little t to big T, then this will be S little t, right? But what is S little t? S little t depends on W little t. Yes. So if you price the stock at any time, then from little t to big T, you will need S little t right here. Sorry, if you price the option, right? You would need S little t right here, but S little t will depend on W little t. All right. So really, it's really the joint that we're interested in. So this is very good. All right. But of course, right, that's the object we're after, but we want it, right? So this is just what we want. So 1 gives us what we want. 2 gives us what we need. 2 gives us, so 2 right here. Gives us how to calculate it. Why? Because we know that B is a Brownian motion. Is that okay? So from the fact that B is a Brownian motion, then I can derive this probability because that's just a normal distribution. Okay. So to recap, right, several things. First, there's this whole idea of explaining what B is. B is a reflected path of the Brownian motion, right, compared to some level. This level right here, by the way, this M is the level of the max. This M is that level of the max that we're interested in. Okay. So we reflect at some level M that somehow that the max we're interested in is there. But anyway, right, forget that for now. The point is that if we define the reflected path in a certain way like this, then the reflected path has a known law, namely Brownian motion. Okay. Then, so why? Well, we explained that. But then after that, right, somehow because of the way we define the reflected path, this identity comes true. This identity comes true is very helpful for us because the joint distribution between the max and the Brownian motion is known via this new Brownian motion. And then we're done, right? And then we're done. In other words, we can establish the joint distribution based on the law of a different Brownian motion. Any question on this? Okay, so we have 5 minutes left. So I would just show you, right, the 2y, this y, and this y, okay? And then we're gonna just continue from next class, in next class. Okay, so y, right, y is the reflected path, right? Y is the reflected process, a Brownian motion. The reason is this, okay? The reason is actually now we need some categorization, that we need to know what is a Brownian motion. And it's a theme that you encounter in this class again and again. we state the definition of brine motion, but sometimes, right, to show that something is brine motion, we don't use the direct definition. We use something else. So here you will encounter yet one more definition. It's called the Levy categorization. Levy categorization of brine motion, which is this. Suppose that we have some process that starts at 0. It's a martingale. Its quadratic variation is t. These three together allows you to conclude that B is a brine motion. Okay. So notice how, right, besides the first one, there's no mention of normality, but somehow these are enough to say that this is a brine motion. So obviously there's a y upon a y, meaning you're like, why is this categorization true? I'll leave this, right, for your homework or for your review worksheet, but basically review session. But basically the idea is this. This is connect with the idea that something is brine motion if and only if right? You learned this before when we do change of measure, that this, right, BT is a brine motion if and only if this is true. And by the way, actually this goes both ways, right? Obviously, if something is a brine motion, then the following is true. So connect this with this. So in other words, what you want to do is somehow to show that 1, 2, 3 here implies this. Then you're done. Because if 1, 2, 3 implies this, then from the fact that you know this is a brine motion, then you can conclude this. Okay. Now I will use the Levy categorization to show that the reflected path right here is a brine motion. Okay. So how do I do that? Well, how I would do this, right, is to apply, right, the Levy categorization to the reflected path okay. I define some process, let me call it A of t, to be 1 if t is less than tau, to be -1 if t is bigger than tau. So remember, sorry, less than. Remember that right here, right, tau is the first time that my original brine motion hits at level m. And B, right, is defined in terms of W in connection with that tau, right? So I claim that the reflected brine motion is nothing but the integral of this process against my original brine motion. So in other words, right, this is equivalent to BT is equal to WT, t less than tau, and W tau minus WT minus W tau for t greater than tau. Right here. These are equivalent. All right. Sorry, these are equivalent. All right. So anyway, right, I'll leave this for you to check as well. But after we have this representation, then we're done in the following ways, right? Then, right, b of 0 is equal to 0 because, you know, the integral from 0 to 0 is 0. 2, b is a martingale. Why? The integral against a prime motion is a martingale. Doesn't matter what this process is. 3, right? What's dB? dBt is a of t dwt, right? The quadratic variation is just dBt squared, right? Which is a square dwt squared. But we say this is dt, right? Because that's prime motion. What's at squared? Well, at is either 1 or minus 1. So this is dt. So therefore, the quadratic variation is t. So therefore, right, indeed, by this representation, the reflected prime motion, the reflected process is a prime motion. All right, so sorry for keeping you holding. So we will continue, right, with proving this identity next time, and from there, obtain the closed form formula, right, for pricing of the, you know, Berry option, and also from that, the look back option. All right, so thank you for joining, guys. I will address any questions you have for homework and other stuff. If not, have a good day. All right.
All right, thank you, Professor.
Yeah, thank you, Don. Okay, any questions you have that I can address? Sharon?
Here. The problem one, it is the same as the one in the third problem in the review session.
Mm-hmm.
And I use the same and I use the same program as it in the review session, and I found that I can't get the call. Let me.
You want to share your screen or something?
Let me rewrite. Let me write again. Oh my God.
What's your problem?
I can't run out.
You cannot run it?
Yes, I cannot define, but maybe I don't know the reason. But maybe I don't know the reason.
Okay.
Let me okay. Let me share my screen.
Okay. So let me
Oh my God.
let me allow you to do that.
Yes.
Okay. Go ahead.
Okay. And here is my program, and it says that the answer is not defined, but actually the answer is this call.
Mm-hmm. Your code.
Why it isn't defined?
Not sure.
Here's call.
I mean, so looking at your code, right? I mean, what do you mean by res equal to something? I saw a line like that. What does that mean? In line 31, right? You have your definition and you have res equal to something. What is that doing there?
No, let me do it again. Oh my God, it is not defined. It is still not defined, but I just would like to use this to put this in.
I'm not seeing entirely your code, Shaoran, but I just noticed that in line 31, you see that your res equal to something. That seems like a line that doesn't do anything. Are you sure? Coding is very strict. If you make any error, your code won't run. What is that doing there? You know what I'm trying to say? In your definition of the call option, what is that res equal doing there?
It makes no sense. It makes no sense.
What do you mean it makes? So if it makes no sense, you shouldn't keep it there.
Yes, I deleted and
Really? I don't see it.
and it is. Let me copy it.
Okay. You know what? Let me see if other folks have any questions, because I mean, looking at your code would be long. So I will get back to you, okay, Sharon? If this is the question.
Let me yes. Okay.
So does anyone else have any question about the homework that you want to ask?
I have a question about homework.
Yeah.
For the problem 2.
Yeah.
Yeah, find the formula for ST. So
Find a formula for ST. Is that the
yeah, I mean find an
compound Poisson
explicit
process?
formula for ST. Yeah. Is it? I think that's the
Oh, no,
third question.
It's not. It's not. It's
Yeah.
not. It's the one without the est part, right? In the
Yeah, exactly.
Yeah. Okay.
So I kind of know what should I do, but just can't figure out a way to solve this question. So yeah, maybe.
Let me see here, right? Let me pull up the question real quick. So unless I'm wrong, right? If I remember correctly, so question 2, oh, I'll need to share my screen with you. Whoops. So question 2 is something like, first at least 2a, right? dst is ast dt plus sigma djt. Is that right? Something like that, right?
No.
No, that was
no. I think that's for a question. I mean, second question. For the first question,
okay, then let me look up. I
it
forgot.
should be. Is it?
It's not. Let me look it up.
Sigma.
Homework 8, right?
Yeah, there's no sigma term in the
Hold on.
second one.
Okay, I see. Okay, so sorry, just DJT then. Okay.
Yeah.
All right. So the problem, right? Say that just use EO's formula, right? So meaning you want to do this e to the minus ATST, right?
Mm-hmm.
And what you will find is that after you use EO formula, you will get e to minus at djt. Because exactly this part cancel. Did you get there, or you want me to show you how to go from here to here?
Yeah. I actually I get the first step of the Ito formula, but I didn't cancel out the the other parts. So
It should be canceled, right? It should be canceled.
yeah, but yeah, what I get is the minus alpha e to the minus alpha t st dt plus e to the minus alpha t dst. So maybe I can extend the dst, and maybe we can work out to cancel out some terms. So yeah.
Yeah, exactly, right? So, but
Yeah.
then
And I think I get there. Yeah.
I don't like the dst part, okay? Because
Yeah, exactly.
you do, but you should be more careful to use the jump process. Here is fine. So you're right, that is minus a, right? E to minus at, right? St, right? dt, like this, right? That's the dt term. And then I will do this. This is the continuous part. Okay, this is the jump part. Okay, so then I would say that then you would do e to minus at, right? D continuous part, right? And then says plus the jump part, meaning st minus st minus. This is the jump part. Is that okay? If you were strict about the Ito's form for the jump process, that's how it looks, right? This is the jump.
Yeah, exactly.
But right, you see that this is the continuous part, which is just a stdt. They cancel.
Okay.
Right? You follow me?
Yes.
So what about the jump, right? What about the jump? The jump part, right? What is st minus st minus? Well, sorry, not
It
st.
should be another term, right?
Yeah, there should be this guy, right? Yeah, sorry. So it should be e to minus at st minus e to minus at minus st minus, right? The jump. But right, of course, this is just e to minus at st minus st minus, or this is just e to minus at delta j. Is that okay? So that's how I got it. Okay. So then, right, after you get this, then all you have to do is to integrate back to get back to the s. In other words, right, your e to minus at st, right, minus s0, right, is equal to the integral, but here, because it's pure jump, right, it's just a sum. 0 less than s less than equal to t, e to minus as delta gs.
Okay.
So that means, right, that st is e to at times s0 plus the sum. And that's your final formula, if you will. You can
Oh, okay.
you can pass
I see.
it, but
Oh, okay. This is
does that
what
make
you
sense?
mean. Okay. Yeah. Okay. I got it. So actually, I almost got there, but I don't know.
There's a
Just
cancellation
get
that you miss, right? There's a
formula.
cancellation that you miss.
Okay.
So do you want me to show you part 2 or?
I'm okay. I'm okay with the part 2, I guess. Yeah.
Okay, very good.
And for the third question, problem 3.
Yeah.
Actually, I kind of I know what the value of a constants, but can we just directly write it down, or we have to prove it?
I guess, right. So actually the value of a constant is expectation of q at 1.
Yes.
Okay. So if you understand why that is true, then I don't care if you have to prove it or not. But if you don't, then for your own benefit, you should at least explain to yourself why this is true.
Okay.
Right. But if you know it, I don't care. That's it.
Okay, sure.
Mhm.
Okay. Yeah, that's all my question. Thank you.
Sure, fine. Anyone else has any question besides coding, which takes a while, so I'll address that part last. No one? Okay, so Sharon, let's maybe go back to you. What you want me? Let's take a look at your code again. You want to share your screen? Let's take a look at your code again. You want to share your screen?
Okay, I will share my screen. My open my mobile. Okay.
Are you sharing? I'm not seeing anything. Are you sharing? I'm not seeing anything.
Oh, I'm sorry. I think I'm sharing, but actually not.
Yeah, now I think it's something. Yeah, now I think it's something.
Here.
Okay, so I see the error.
So
P is
I
not
see the
defined.
error in the P is not defined.
That's not the one that you're talking about, right?
That's not the one that you're talking about, right?
Yes, that's a problem too in the review session, and here is the problem series program.
Okay. Can you scroll down? I still see problem 2.
Okay. Can you scroll down? I still see problem 2.
Sharon, did you scroll down?
Sharon, did you scroll down?
Yes, I'm scrolling down.
Oh, somehow I don't see that.
Oh, no, I don't see that.
Oh my god. Or let me send it in the text form to your email.
Okay, all right. Yeah, I may be able to run it.
Yeah, I may be able to run it.
Okay, let me send it in the text.
Mhm. Jovan, can you run the code for question 1? Okay.
Jovan, can you run the code for question 1? Okay.
Actually, I didn't, start working on that question.
I didn't,
Okay, I see. So I just wonder if
question.
anyone else has any problem with
Okay, I see. So I just wonder if anyone
code
else
for
has
question
a
1.
problem with
Okay, I just said,
Yeah, I just
look into it.
Sure.
Sure.
All right, so let me see. Maybe I can open up your code,
All right,
Sharon.
so let me see.
Give me a
Maybe
moment.
I can open up your code, Sharon.
Okay, let me. I'm opening my email. Okay, I have sent it.
Okay. Oh, I see why. Sharon, I mean, just simply looking at your code, right? You define the S0 after your.
You define the S0
Oh, hold on.
after
Let me
your.
see. All right, cool. Let me see.
Oh,
here.
hold on. Let me see. All right, cool. Let me see here.
Mm.
Right. So let me share my screen.
So let me share my screen.
Mm.
All right, this is your code, right?
Yes.
I would normally just put this up. Okay. And let's see if we run it, what happens. Local variable reference before assignment. So right here, that's the error, right? So that's because you must define res first. It should be something like res equal to 0.
Oh.
So let's run it.
Oh.
Hold on. Wait. I think you might have the same error.
You might have the same error
Here, right? Wait, hold on. Why do you have two
Let me-
definitions right here?
Let me take a.
Why do you have two definitions right here?
Are they the same?
Oh.
Are they the same?
I pasted for more time.
Why? Definition is definition, right? You don't need to define it four more times.
Definition, right? You don't need to define it four more times.
Oh.
Okay, so let's see.
Yes, I know, but I made a mistake and I pasted it for more time.
Call price 1 is not defined.
What's not defined?
Wait, you mean just call, right?
Wait, you mean just call, right?
Oh yes, just call. No call price.
There you go, something like that.
There you go, something like that.
Let me see. Okay. But why it is only oh.
It's taking a while.
And
Okay.
for the PDF.
Okay.
And for the PDF, it is not 0.
For the what? PDF?
And for the PDF, PDF, yes. Let me take a screenshot for this. Let me take a screenshot. And the part B is that we should verify the PDF. We should verify.
You mean the PDE?
The PDE.
Yeah.
But it is not 0.
Did you try? Because before your code doesn't run yet. Are you sure it doesn't work?
Your code doesn't run yet. Are you sure it doesn't work?
Let me see. Let me try it again.
So what do you need, right? V is call this.
What do you need, right? V is call this.
Data, right? It's
Data, right? It's.
Oh, I don't want to call that.
I don't want to call that.
Let's say called BT.
Let's say call
BX.
BX.
Delta.
Delta.
Yes.
And Then Vxx is your gamma.
Then Vxx is your gamma.
Yeah.
And then what else do we need? We need, so,
And what else do we need?
so
we need
PDE, right, is
so
minus R times V
PDE, right?
plus
Yes.
Minus R times V
VT plus V sub X
Vt plus V
times
sub X
X0 plus 1/2
times X0
X
plus
times
half
sigma square
X
Yes.
sigma square
S square. And then what is it? What we have?
S square. And then what is it? What we have?
We have something about the jump, right? What was the equation?
We have something about the jump, right? What was the equation?
1 second here. The
1
equation
second
is,
here.
Mm.
The equation is
something like the call.
something like the call.
Right, lambda tilde times a call minus call.
Right,
Like,
lambda tilde times a call minus call. Like.
so, okay, so let's see.
So, okay, so let's see.
Mm.
So you call it lambda, right? Lambda times.
So you call it lambda, right? Lambda times
sigma
sigma
minus
minus
V.
V.
This is this.
Like this.
The lim tau is not defined.
Lim tau is not defined.
What is tau doing here?
What is tau doing here?
You mean T, right?
Oh,
T, right?
yeah.
Ooh.
Ooh.
Oh my God.
Oh, R minus lambda tilde times sigma.
Oh, R minus lambda tilde times sigma.
Yes. Now that's too small. So let's see.
Now that's too small. So let's see.
Yes. But it's not zero.
I know. So you have to, the whole point you have
I
to play
know.
with it.
So you have to, the whole point you have to play with this.
The equation must be correct, all right? So
The
when
equation must be
something like
correct,
this,
all right?
then
So when
there's
something
some
like
error
this,
in our code.
then there's some error in our code.
So I have to go back and look at, like what you have
So
here.
I have to go back and look at, like what you have here.
I think most of the point you got is
Yeah.
fine, but
I think most of the point you got is fine, but
delta gamma. Let me see what the gamma you have here.
let me see what the gamma you have here.
Mm.
Yeah, looks fine.
Yeah, looks
Theta.
fine.
I think
Theta.
maybe theta doesn't
I
have
think
minus. Let me see.
maybe theta doesn't have minus. Let me see.
No.
No.
Tau.
Tau.
Your code seems fine.
Your code seems fine. I
don't see an error in it.
don't see an error in it.
Minus RV.
Minus RV.
Piece of T.
Piece of T.
Oh, hold on. It is really not. There's no minus here.
Oh, hold on. It's really not. There's no minus here. Okay.
Wait.
Wait.
Plus T.
Plus T.
By
By.
Let me try this.
Try this.
No, there's something that's off.
No.
Oh my god.
There's something that's off.
So you know what? Let me take a look at this. Right? It's roughly
So you know what?
something like
let
this.
me take a look at this. Right? It's roughly like this.
There's something that we need to kind of
There's
probably
something
some error somewhere here that
probably some error somewhere here that
V and VT use T.
V and VT use T. But
I think here her T and her tau are the same, right?
I think here her T.
Let me see if that makes any change. Thank you, Mao. Let me see if that helps. Yeah, it doesn't change that.
Oh my god. So that let they all use T.
Yeah, so I mean, I probably will have to change everything back to T.
Yeah.
I feel like there's some small error here that trips the whole thing up. I don't know what it is. I you know, catching bug is harder. Did anyone code this and get the right answer? Get to be zero?
Get to be zero.
So let me look into this, all right, and then I'll
let me look into this, all right, and then
I'll tell you. I mean, I can say that roughly this is the idea.
I mean, I can say that roughly this is the idea.
Something is off somewhere. I cannot.
Something is off somewhere. I cannot.
You get strange number as well. Okay.
You get strange number as well. Okay.
I mean, there's a small chance that our PD is wrong.
I mean,
but I don't think the PD is wrong.
But I don't think the PD is wrong.
So I have to think a little bit more carefully about this, right?
So,
I mean, if you don't verify it, just go and submit it.
If you don't verify it, just go and submit it.
If the mistake is on my side, meaning that if I told you something wrong, then of course you won't lose any point. Okay, that means you know, I just told you something wrong. There's a chance that there's some error from what I told you.
There's some error from what I told you, but
I doubt it. So let me check. Okay, I mean, this is not something I can solve here. This is all I can tell you up to here.
I mean, this is not something I can solve here. This is all I can tell you up to here.
All right. So yeah, go ahead and try your code the best you can.
All right. So yeah, go ahead and try your code the best you can.
And if it doesn't add up to 0, that's fine. If you cannot catch anything,
If it doesn't add up to 0,
that
that's
means
fine.
that there might be an error in theory. So I will
There might be an
go
error
back and address that.
I will go back and address that.
I have wrong. I have wrong a number, but I have wrong number. It is this. It is this. With year.
No, that's too large. I mean, right here, right, is what I
No,
get.
that's too large. I mean, right here, right, is what I get. See?
Okay, so yeah, I will look into this, and now I'll let you know.
Okay, so
Maybe
yeah,
I'll if I figure out a quick
I'll-
fix, then
I'll let you
I'll send out an
Maybe
announcement.
if I figure out a quick fix, then I'll send out an announcement.
Okay.
Anything else?
Anything else?
No. Let me write it by myself.
Thank you, Mel. Yeah.
Thank you, Mel. Yeah.
And thank you, Professor.
Yeah, thank you. Thank you. I'll look at this.
Yeah,
all right?
thank
All
you.
right.
Thank you. I'll look at this. All right. All right.
Okay.
Yeah, thank you.